There we go. Okay, so remember, if y equals f of x, then the average rate of change can be given by this change in y over change in x. So remember, we're seeing it more like this. But that essentially means the same thing. I think I've said this before, but just in case you've forgotten or I didn't mention it, that delta symbol can be thought of to mean as change in. So we're thinking of a change in y over change in x here. So that means for small x, say the small change in x, I should say. Say the change in x is really small. Nudge, nudge, wink, wink, like something between 3 and 3.001. If the change in x is really small, then we've kind of already seen that the derivative value can be approximated by that change in y over change in x. That's essentially what we were doing in 2.1, is we were taking this average rate of change for a very small change in x and estimating the derivative with it. So what that also means is if I do a little bit of algebra here and I essentially, multiply both sides by this change in x, I could get here and this is going to be the basis of an idea that we're going to use towards the end of 2.3. Whoa, I'm throwing things. Towards the end of 2.3, so you're probably going to forget it by the time we get there. But essentially, this is going to allow us, this is essentially going to link up to something called tangent line approximation. So I'm going to write that down now, so if you're looking at it later, you can maybe see the link between the two if my pen would stop being silly. Stop it. What's happening? Come on, pen. You can do it. I believe. Oh no. Why? Don't do this. Here we go. Or maybe not. Oh no. What have I done? Why is this not working? Oh, this isn't good. Oh no. All right, then sudden switch, because yeah, this isn't, why now? Why now do you decide you don't want to work? Okay, never mind then. Give me 1 second, guys. I do this, and then I've got to. Oh, that's not gonna reach. Yes, it is. So let's do. Sorry. Okay, give me 1 second. I had to completely switch. I guess it's good that I magically have 2 tablets, otherwise that would have not been good. But now I've got to go and find the notes again. Sorry guys, 1 second. Don't we all just love online learning? It's so much fun. Y'all still hear me? Yes? Okay, thank you. Because I pretty much changed everything over. The camera's on the other one. The mic's over here now. Everything's dying. And of course, my older tablet is obnoxiously slow. So it's taking 5 years. Oh my God, come on. You can do it. I believe in you. It's so old. It's trying so hard. Almost there. Come on. There you go. And now back over here and share it. So what did I already write down? I already wrote. Oh, and now this one's gonna lag like nobody's business. Oh, today's going to be so fun. What was I saying? I was saying this is going to be referred back to something called tangent line approximation. We're going to define that later. So that'll kind of come back, but just so you kind of get an idea of where it came from. It came from this idea here. So they're still recording. Okay. So the first thing we've got to talk about first, though, is something called Leibniz notation. Oh, there we go. So Leibniz notation, a little bit of history. Calculus was essentially created by two different guys at the same time, but they didn't know that the other person was also creating calculus. So there's essentially two different types of notation that are used. We mainly use Newtonian. Leibniz notation is used a bit more often in a general calculus course. But in terms of our course, we do talk about it a little bit because it kind of mirrors this idea of this instantaneous rate of change as a slope. And that's because the Leibniz notation for the derivative is this guy on the right, this dy over dx. Now, the reason we're going to use it is because it's actually really helpful with determining the units of a derivative. If I just write like f prime of x, it might be difficult to remember how the units go, but writing it as dy over dx usually makes it a bit easier. So if I were to read this, you'll often hear me say dy over dx, like that is a way that most people read it, but the official way to read that would be the derivative of y with respect to x. And as I've already said, the notation is especially helpful in determining the units of the derivative. So the units of the derivative are going to be the units of the dependent variable, which I'll put y in parentheses because that's usually the more familiar one that we're used to using, divided by the units of the independent. Yep. Let me just finish writing this word and then I will reshare it. Boink. 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 There we go. So units are the dependent divided by the units of the independent. Now, of course, we don't always work with x and y, so that's why we don't necessarily state them in terms of x and y. But so in general, say you have dA over dB, so you have a derivative, then the units of that would be the units of A divided by the units of B, which is kind of why we use Leibniz notation to help us figure out the units, because if you have that Leibniz notation, it kind of just falls out. So that's a thing. And then if the derivative of a function is not changing rapidly, and I'll kind of explain what I mean by that with a picture in a second. If it is not changing rapidly near a point, then the derivative is approximately equal to the change in the function when the independent variable increases by 1. Now, this idea in general is something that we kind of already know. The wording just might be throwing you off. If you think about what the slope of a line means, and I've kind of talked about this before when we were interpreting it, like way back when in chapter 1, the first time I ever interpreted it, is remember slope is like rise over run, right? And if you're very particular, you could take the run to just be 1 and your rise to be the total slope value. That's kind of what this is talking about here, is that the derivative is essentially going to tell us that slope value of that, kind of line. If we go over 1, how much did we increase by? Now, what does it mean by that changing rapidly thing? Say we have something that looks like this versus something that looks like that. And say I wanted to draw some tangent lines. say I have a tangent line right here. So that'll look kind of like this. And say I have a tangent line right here. So that'll look kind of like this. So kind of in our option on the left, if I kind of start at that point that the tangent line is kind of 4, if I move over kind of, one space to the right, if you will, where, how large one space, what words were trying to come out of my mouth? I'm kind of just making up the distance between the 2 points, but say I kind of jump over to the right a little bit. That distance between the actual function and that tangent line, it's still really, really close. Even if I go, another kind of step over, it gets farther away, but it's still not that bad. So like I could kind of just say that the function is going to be approximately the same value of that tangent line for a little bit. Whereas if I go to kind of my option on the right, if I kind of jump over one, well, that's already kind of starting kind of large. Like it's about as close as kind of this second. Oh no, no. There's an undo button on here, right? No, there's no undo button. What if I hit Control Z? That means I have to reattach my keyboard. Control Z doesn't work. Oh no. Okay, let me redraw that really quick. Oh, what is my life today? And then, oh, good enough. Okay. Okay, what the heck was I saying now? So it's about as far away as kind of this second point was on the left option for the first one on this right option. But say I go over one more on, this right thing, then it starts getting, really far away. And if we even compare just, how close that kind of first step piece was, the one on the left is much closer than the one on the right. So essentially this idea of changing rapidly is the function increasing very quickly or decreasing very quickly? If it is, then the tangent line isn't going to do it much good. But if it's kind of a situation where it's kind of increasing or decreasing very slowly, then the tangent line is actually going to do a pretty decent job of kind of approximating what the function's doing. And we're kind of going to use that idea. Again, we kind of take a step away from it for a second and then come back to it later. So when we get to the tangent line approximation stuff in a little bit, this is also kind of pulling on that idea. Excuse me. Now back to Leibniz notation really quick. Now, one of the downfalls to Leibniz notation is when you're trying to write something like f prime of 2. Because Leibniz notation does not write that as nicely. If I want to write something like this in Leibniz notation, it's going to be dy over dx. You have this like little line, and then you say where the value is. So definitely not as pretty and clean as f prime of 2, but that's how you would do it. So now what I want to talk about, and kind of the main point of one of the main points of this section, is interpreting the derivative. Technically, we've already talked about this a little bit already because we've been interpreting slopes and the derivative is a slope. But let's kind of officially write down kind of how we can do this interpretation. So we kind of have those two choices that I've talked about a little bit already, the rate way and the step way. But now what I want to do is I want to write out essentially the 3 things you need in either case. So in either case, if you're trying to interpret a derivative, you need, well, how about I phrase it like this? You must include 3 things in your interpretation. In either case that you go in, it's always these 3 things that you need. So we kind of have our rate way and our step way. Remember, the step is kind of that idea of the slope of the line being over 1 up however many. So the first thing you need in both of these is you always need to state the starting x value. In both cases. So let me try to do like a mini example down here along the way. Maybe up a little bit more. Or say I have like f prime of, let me put the example in the middle. Boink, boink. Say I want f prime of 5 being 200, where this is a year and this is a change in population. And say it's in years since 2010. So I know it's kind of really tiny down there. So essentially in both cases, we would have to say in 2015, if I kind of use that example down there, because that starting x value is 5, since it's 5 years since 2010, I would say in 2015. So I would start interpreting both of those in either, case, as you'd have to essentially tell them where you're starting at. If you want to continue with the rate way, the next thing you essentially have to say is you have to state the direction the y is changing by. And by direction, I mean increasing or decreasing. And that's essentially based off of whether or not the value for the slope is positive or negative. Let's just say this is in general people. So that would just be 200 people per year. So if I was continuing on this kind of interpretation on the left, I would say in 2015, the population is increasing. Can I just abbreviate increasing because I'm running out of space? And then how you finish it is you state the derivative value with what I like to call rate units. It's not really the formal way to phrase it, but I think it gets the point across. What I mean there is this derivative has units of people per year, if I'm going with this little tiny example that I'm kind of working with down here. So if it's in people per year, I'd say the population is increasing by 200 people per year. I'd essentially use the units of that actual derivative value. And there's a difference because in the other type of interpretation, you use a different type of unit. That's why I like to differentiate and kind of pull attention to what type of units it is. And this is, again, a tiny bit of a review, but I don't think we've ever written it out in this much generality, so here it is. Whereas if I want to go the step way, the second thing I need for the step way is you need to essentially state that you add one x value. So in this case, the x values are years. So essentially I'd say something like for each additional year, or you could say something like if I add 1 year, or if we increase by 1 year, or if we, or something like after 2015 in 2016, if you just wanted to make a note of the next year would be 2016. And you finish that by stating how the y value increases. Or decreases, depending on the sign of the derivative value. And here you're just going to use what I call y units. So it's just the units of the Y value. It's not that rate unit anymore. So if I wanted to finish this out, I'd say in 2015, for each additional year, the population increases. I'm going to abbreviate increases, kind of running out of space, by 200 people. And just people, not people per year. And I know that I kind of squeezed that in there. It's because I wasn't planning on doing that example at the bottom. That wasn't part of my original notes, which is why this is so squished. But there we go. So again, kind of had these setups presented already, but we never wrote them down in full generality that you can kind of go back and look at later. So here's kind of the setup of how you want to interpret derivative values or slopes. I'm going to leave that up for like 5 more seconds in case someone's still getting it down before we go down and do a couple examples and then talk about tangent line approximation. I'm trying to leave that up for a tiny bit longer while I read this question, but I am going to need to scroll down to write it all out. But anyway, so now this example is a bit tedious on the units. The units are kind of bleh, but I also think it's really good practice because of the fact that they're kind of crazy units, because it just kind of forces you to take these kind of obnoxious units and make sure you're putting them in the right spot. So say we have Q equals F of P gives the number of thousands of tons of zinc, so that's one of our units, produced when the price is P dollars per ton. So that's our other unit. Then what are the units and the meaning of, now I'm going to rewrite this. First of all, because I should always put zeros in front of these decimals, and I always forget. But also because I think it's so tiny that you can't tell which one's the Q and which one's the P. So we have dQ over dP when P is 900 is going to be equal to 0.2, and we want to essentially state the units and interpret that. Now in this specific case, I'm going to do both of the interpretations in both ways. After this one, I'm just going to pick and choose kind of between the two. Sometimes it's better to write it in one way or the other, and I'm going to pick the one that's better because I know that that's the one that's better. But in terms of in general, you get to pick whichever one makes you happy or whatever floats your boat. But in terms of some of the examples we have coming up, to kind of focus on what comes next, one of them is better than the other. But anyway, so first thing is let's just talk about the units. Well, if I think about the fact that this is a dq over dp, if I talk about the Leibniz notation, well then again, the Leibniz notation is kind of nice because the units just kind of fall out for us. It's going to be the units of Q, which was kind of tedious. That was the thousands of tons of zinc. What? Is it my pen or my... No, do not do this. Okay. I was about to throw everything out. What was I writing? Thousands of tons of zinc. And then our units of P are dollars per ton. I meant it when these units were a bit crazy. But it's okay. So those would be our units of the derivative, thousands of tons of zinc per dollars per ton. It's also very weird to say. So say I want to interpret this, and I have my two options, and again, for this specific example, I'm going to do both. If I wanted to do my right way, well, the first thing we need to do is essentially state where we're starting. So what is the starting P value in this case? Well, that would be the 900. So I usually like to just use the word after the starting X value. So I would say after $900 per ton, then we essentially tell us whether the Y values, the Q's in this case, are increasing or decreasing. Well, my derivative value is positive, so we'd be increasing. So essentially the amount of zinc is increasing. So the amount of zinc is increasing by, and then we state our derivative value with the rate units, so with the units of the actual derivative, so that obnoxious thousands of tons per zinc per dollar per ton. So thousands of tons of zinc per dollar per ton. Again, I know it sounds weird, but those are our units. So that 900 can look a lot nicer. And then if I wanted to go the other way, the other type of option I have for my interpretation, then we would say after 900, we always start with our starting value. So after $900 per ton. But in kind of that step way, now we just say that that value is going to increase by 1. So if we say something like increasing by $1 per ton will increase, and we want to talk about whether the Y values are increasing or decreasing. Again, they're increasing because 0.2 is positive. So we'll increase by 0.2, but now we just use the units of Q, so thousands of tons of zinc. Of tons of zinc. The reason why we don't need the rate units here is because essentially we're taking care of the units of Q at the end, and then the units of P we're actually taking care of kind of in this like addition step, if you will, the part where we're telling them to increase the X by 1. That's kind of where the X units come in, and then the Y units come in at the end. Whereas in the other interpretation, we don't really state the X units anywhere, so they have to get tacked on to the end as part of the rate, if that makes any sense. So again, either of these two is fine, whichever type floats your boat. Also, I'm not a huge stickler for phrasing. I'm a math person, not an English person. I can't spell, my grammar is horrible. So as long as you're getting the point across, I don't really care. Also, it's if you follow that kind of process that we wrote down of start with the X value, tell me whether we're increasing or decreasing, state the derivative value, you'll be fine even if it doesn't sound like decent English. As long as you're following the correct format and it gets the point across. I don't really care if it sounds horrible or not, because I know for sure some of the things I write don't sound like English. I'm pretty sure in one of my past semesters I wrote down what I thought was a complete sentence, and someone was like, that's not a sentence. And I was like, what? What do you mean? And they were like, you never finished your sentence. And I was like, I thought I did. Apparently I didn't. I'm not good at writing. Anyway, so that's that one. So let's look at a different one now, if there aren't any questions. We'll wait for a couple seconds. Okay, so say we have the cost in dollars of building a house that's A square feet in area is given by the function C equals f of A. What are the units and the practical interpretation of the function f prime of A? So it's a bit weirder because we don't have any numbers. We don't have any set numbers here. We're just going to give kind of a generic interpretation. So it's almost like we can't use that process anymore. We can kind of follow it, but it doesn't quite fit as often now because we don't have a starting X value. We don't have an actual derivative value. We're just kind of trying to figure out what that would mean if we were given values. But let's focus on the units first. So we have f prime of A. So let me look at that in Leibniz notation first, because if I want to look at the units, let me look at Leibniz notation. Well, if I think dy over dx, but here I have a c and an a, well, which one acts as my y value? That would be the c value here, so we would have dc over dA. Once my screen catches up. There we go. So the units, well, what are the units of c? That was in dollars. What are the units of a? Square feet. You could write that as, what it really should be written as, but I usually just write out square feet. So our units are dollars per square foot. If you wrote square feet, whatever. but technically the phrasing is really usually said in dollars per square foot. But anyway, so if we think about what that means just in general, because again, we don't have any values here, what would this derivative value actually tell us? And I think in this case, when it comes to this context and it being general instead of actually given values, I think the step way makes a bit more sense. So essentially we have a building that is a square feet. And what that value of f prime is going to tell us is essentially how much more it's going to cost us to build another square foot. So if we have a building that's a square feet and we want to make it 1 square foot larger, the f prime of a value, whatever it is going to tell us that extra cost. So the interpretation would kind of be something like f prime of a is the cost of building 1 more square foot, 1 more on a building that is a, and I'll write square feet like that. You could also think about it as, and you might say, well, why didn't you do this one first? Because it's less words, but whatever. You could also think about it as the cost per square foot. That would kind of be the rate interpretation. But I think the rate interpretation doesn't necessarily come as quickly and intuitively as just thinking about if I add on an extra square foot, it's telling me how much the cost is increasing by. Or maybe you get it right off the bat, whatever floats your boat. Again, between the two of them, you never have to really choose one over the other. But you do want to, I should stress, while you kind of get to choose one or the other, you do want to be familiar with both, especially for Wiley. Not necessarily for me, but especially for Wiley, because sometimes Wiley sets up the interpretation, say it sets it up like the step way, sorry. So you have to at least be familiar with it enough to be able to fill in the blanks in the right way. But in general, you kind of get to pick which one of the two interpretations makes you happier. Questions, concerns? Before we go on to one more of these, before we go on to change of line approximation. Savvy. Let's do one more interpretation one then. So say we're given time L, and wait, I scrolled too far. So time L is going to be in hours that a drug stays in a person's system is a function of the quantity administered in milligrams. So L equals F of Q. Interpret the statement